Hiya, Snuffles again here. So, the video I posted up about shift registers, I sat here playing with the circuit and adding things to it and seeing what we could make it do. I came up with this example, which is probably a very rough approximation of what might be happening with those keypads. So, we'll have a run through this. That's my chair squeaking there. So, what we've done is everything this side would be our keypad, and everything this side would be our micro. Let me just shut my phone up because I didn't realise it was there. There we go. And we'll wait for the motorbike. So I'll go through exactly what's going on here, but I'll show you what this does. So we have a display here, although you can't see much going on these data lines here. This is actually ramped up to a reasonably high speed. If you look, you can see that it's not necessarily doing a good update, but we've got sequential counting going on here, and it just doesn't update the screen as fast as the logic is going on. We're above what can really easily be rendered. You can see the shift registers are going nuts. So what we've got here is a 7-segment display. If I hit this shift button here, oh no, that's the right tool. So if I hit this shift button over here, you'll see we change the display. That shows you the update. And then you can see, if you look at the LEDs over this side, they correspond to each of these buttons. I have to hold the buttons down a while just because of the speed of what's going on here. So effectively we have 8 segments per 16, 32. We've got 64 individual segments here. We've got 16 buttons here being driven with 4 lines. So yeah, that's probably fairly close to what's going on. We've got a common clock and a common reset line. I don't think the Sony panel does have that. I think they've got separate reset and separate clock lines for everything. So we'll start at the beginning. We'll go full loops. We'll go round this way to the displays and we'll go back. So we've got our same clock here that's generating our synchronization pulse. We've also got another counter here. Now if you see, this one only counts up to 7, and that is outputting a 4-bit that is a 4-bit counter, which is outputting 4 bits here, which are used to work out where we're going to look in this ROM. We'll come back to that in a second. So we've got a multiplexer here which generates the 8 selects that we actually need to select the displays. And as you see, as that counts up, you'll see our selects are going. Our selects are busy here. I will go into this when we get over here because this isn't the way you do it in real life. You might do, but it isn't the easiest way. So that generates our selects, and then we'll come back to the shift as well. So our selects go out to the shift register. So these 4 bits are used with this shift input to select an address in the EEPROM, and as you can see, what we're doing is adding the value of this bit to these, adding the value of this bit to the output of the counter. And if I press that shift to turn it off, you can see we're looking from 00 to 08, which gives us our 8 characters, and you can see there is data in here. When we shift, you see that it asserts that adds 10. Sorry, that adds 16 to the address, and you can see we're now looking down here at these. The 8-bit data out of here is then combined with the 8 bits out of the demultiplexer. That gives us our 16 bits, which is fed into our parallel to serial converter, and then this is pretty much the same as we were doing with the other one. So we're into the serial parallel converters, we shift them out, we lock them into the latches, we use sync pulse to latch the data in, and then you can see what's going on here. So if you look at these numbers, they will match where we're reading, what's currently in the EEPROM address that we're reading, and this represents the select. So here's your selects going in, here's your selects going out. Now what you would normally do is these would drive transistors, and these would drive either the common cathode or common anode on the display, with the drive for the segments coming from here. As you can see, something very similar is happening, but we're having to latch the segment data into here. This is because the provided 7 segments here don't provide any method of latching the data in. So what you'd actually have here, instead of this mess with all the latches and all of this mess down here, is literally data flowing to all the segments, possibly with a depending on what you're using to drive them, possibly with a transistor per segment, and then a transistor per display to drive the common cathode or common anode, and then you use persistence of vision. The drawback with doing it that way is the moment this clock stops or something happens, this display will freeze. Done this way, we're driving these as DC, which means we don't need the clock, we don't need the constant scan. So that's how we're driving the display there. For the buttons, all we are doing is each one of these buttons represents a single bit on the input to the shift register. If you look up the shift register as I press the buttons, you'll see these are then shifted out using the same clock that we're using to shift data in. We are using the synchronization pulse that we're using to latch the data down here to load the data into the shift register. That comes onto this 4th line, which is a new one, and then this follows this section in reverse here. So we go into the latches here. Again, if I press a button, you'll see that shift in, or you won't because it's not quick enough. But you can see there in that latch, if I hit this, you'll see that changing. And then all we're doing is again using the synchronization pulse to latch the data in, and then down a bus into there, and the LEDs reflect everything. Now what we're doing with the shift key here, if I press that, you'll see we go to shift. We have a D-type latch here. So the way the D-types work is when you wire the D-type like this, sorry, D-type flip-flop, D-type latch, whatever you want to call it. Every time you hit this clock, then the state of this will change. So if this is 0 and you hit this with a 1, which we'll do now, that will go high and it will stay high. If we hit it again, it will go low and it will stay low. And then this generates the 5th bit for our EEPROM. And that's how it all works. It's, if you think, you know, there's a reasonable amount of work going on here and adding things to this. So you could use these to select programs. You could shift extra bits into the EEPROM to provide your, I keep saying EEPROM, you can provide extra bits to the EEPROM down here to provide you with feedback as to what's done. Again, you can use the latches to do that. You can get a fairly concise sort of operators panel without actually using a micro anywhere in here. This is all being driven by logic. The only thing in here that's going to require any reasonable amount of work is going to be this EEPROM. And it does seem a bit of a waste for the sake of a few bytes to use an EEPROM, but there you go. This display here is giving us the row and the data going out, and again you'll see that reflects what's being read. But yeah, there you go. That's a really simple sort of like control panel type layout. Again, it would be easier to do this with the real thing. There would be less components involved. You wouldn't have these registers here. You wouldn't have these registers here. You would be driving these with transistors rather than this way. The wiring would be much more simple. But obviously you've got 64 bits of data coming to this panel, 16 bits of data going from the panel, and you're only using 4 lines still. So it's an incredibly useful thing. And if you're driving this from a micro, then all of this over here you don't need. You can generate this from the micro. Anyway, I hope that's something slightly interesting, and enjoy.